Let us start with a quick recap of the algorithm design strategies we have covered till now. We started with decrease and conquer. Closely related with decrease and conquer, but achieving better running time is divide and conquer. Then we discussed about another strategy. I call that enumerative search. Or we may even enumerative search is one version of exhaustive search. In decrease and conquer and divide and conquer, a problem is decomposed or deconstructed into a few subproblems. In decrease and conquer, typically a problem is deconstructed into one subproblem, whereas in divide and conquer, a problem is deconstructed into a small set of subproblems of roughly the same size. Whereas in exhaustive search, a problem is deconstructed into all possible subproblems. Therefore, there is a world of difference in the running time between the first strategy, decrease and conquer, divide and conquer, and exhaustive search. Whereas the running time of decrease and conquer and divide and conquer is polynomial, the running time of enumerative search or exhaustive search is exponential. If you want to distinguish between decrease and conquer and divide and conquer, we can go a step further and say for decrease and conquer, typical running time is polynomial, whereas divide and conquer improves it, improves even polynomial running time. Since enumerative search or exhaustive search considers every possible subproblem, and generally there is an exponential number of subproblems, the running time is exponential. It is, as I said, mostly useless. Only for small input size, an exponential running time algorithm is useful. When the input size is even a little larger, exponential running time algorithms are useless. Our next algorithm design strategy is positioned somewhere between decrease and conquer and exhaustive search. At one end of the spectrum of strategies is decrease and conquer. At the other end is exhaustive search. And in between, we are going to introduce another algorithm design strategy called dynamic programming. This big picture is very useful. How do we position decrease and conquer, exhaustive search, and dynamic programming? You can imagine here you have decrease and conquer, here you have exhaustive search, and in between you have DP. The motivation for dynamic programming, I have not explained what is dynamic programming. Let's say strategy 1, strategy 2, strategy 3. The motivation for this new strategy comes from exhaustive search. Exhaustive search is implemented using recursion. And it results in a large number of subproblems. But several of the subproblems are identical. They are duplicates. When a number of subproblems are duplicates of one another, do we have to solve them every time we encounter a subproblem? The answer is no need. If a subproblem has a number of duplicates, solve it only once. Why should we solve it every time there is a duplicate subproblem? If we implement the strategy of solving a subproblem only once and never solve a duplicate subproblem, this strategy is the crux of what we call dynamic programming, and therefore we have titled that recursion without duplication. Okay, this is only an overview. We will see with examples what we mean by recursion without duplication and what we mean by dynamic programming is motivated by exhaustive search. These are some of the problems that we will discuss. We will come to it later on. Let's start with a very simple and known problem. Calculating the nth Fibonacci number. Fibonacci number can be defined by this recurrence relation. F of 0, the 0th Fibonacci number is 0. The 1th Fibonacci number is 1. After that, f of n can be expressed as f of n minus 1 plus f of n minus 2 for all n larger than 1. This recurrence relation can be directly translated into a recursive algorithm as shown here. Algorithm fib recursive. It takes one argument n. Input is a non-negative integer. N is greater than or equal to 0. It can never be negative. Output is the nth Fibonacci number f of n. Translate the recurrence relation directly. For case 1, if n is equal to 0, then return 0. If n is equal to 1, then return 1. Otherwise, return fib bar of n minus 1 plus fib bar of n minus 2. You will recall when a if clause ends with return as the last statement, there is no need for else. There is no need to write this as if n is equal to 0, then return 0 else if. I mean, that's how actually you should write. If n is equal to 0, then return 0 else if n is equal to 1, then return 1 else return f of n minus 1 plus f of n minus 2. This is how you should write, but I said this else is not needed, this else is not needed because the last statement is return. The last statement of the if clause is return. Okay, this is just a note. Let us trace how this recursive algorithm evolves when it is called with an argument. Let us trace the execution of this algorithm. Let us trace the recursive process. Suppose we call the algorithm with the argument 6. F of 6 is equal to f of 5 plus f of 4. F of n minus 1 plus f of n minus 2. This is the first call. This is the second call. F of 5 will issue two further calls, f of 4 and f of 3, because f of 5 is equal to f of 4 plus f of 3. So this is the third call. F of 4 will result in two further calls, f of 3 plus f of 2. So this is the fourth call. F of 3 will result in f of 2 plus f of 1. This is the fifth call. F of 2 in f of 1 plus f of 0. These are base cases. f of 1 will return 1, f of 0 will return 0. So this is the 6th call, this is the 7th call, this is the 8th call, this is the 9th call. F of 2 is equal to f of 1 plus f of 0. They are base cases. This is 10, this is 11. Okay, then this is the 12th instance, 12th recursive call. F of 3 is equal to f of 2 plus f of 1, therefore this is 13. F of 2 is equal to f of 1 plus f of 0. They are base cases, 14 and 15. This is 16, this is a base case. This is 17, 18, 19, 20, 21. They are base cases. 22, this is a base case. 23, f of 2 is equal to f of 1 plus f of 0. This is 24, 25. Then f of 6 returns. This is what I mean by tracing. Trace an algorithm. This will trace the recursive process. Trace of the recursive process. How many subproblems are there? If the problem is f of 6, you should answer the question. If the input size is 6, if the problem is f of 6, this is the problem. This is a subproblem. This is another subproblem. Carefully answer my question. For problem f of 6, how many subproblems are there? What is the number of subproblems?
2 subproblems.
Pardon me?
2, sir.
No, I don't hear you well.
2.
Oh, to solve the problem f of 6, how many subproblems do we need to solve?
2, sir.
Which in turn splits into other more and more subproblems.
Yeah. So
eventually result in 24 subproblems.
Yes. Therefore, you will say the number of subproblems is equal to 25 or maybe 24. Including the problem, it is 25. To solve f of 6, we may need to solve only f of 5 and f of 4. To solve the problem, we have to solve only 2 subproblems. But the 2 subproblems are not base cases. If the 2 subproblems f of 5 and f of 4 are base cases, then we may say totally we solve only 2 subproblems. The question is, in all, totally, how many subproblems need to be solved? The answer is 24. Now let us take a look at a good look at this answer. What are those subproblems? F of 6 is a problem. Okay. F of 5 is a problem. F of 4 is a problem. F of 3 is a problem. Subproblem, I mean. F of 2 is a subproblem. F of 1 is a subproblem. F of 0 is a subproblem. Let me ask this question. Are all these things, f of 5, f of 4, f of 3, f of 2, f of 1, f of 0, are these the only subproblems, or do we solve any more subproblems?
These 6 are the only subproblems present in the
only subproblems.
Yeah.
But these subproblems are repeated again, and so that's how they become
correct.
Dependent.
So if I count this, I will say there are only 1, 2, 3, 4, 5, 6 subproblems. So let us take a look at the question that we asked first. To solve f of 6, the given problem, how many subproblems do we need to solve? 24 or 6?
6, sir.
Sir, actually,
It depends on the algorithm that we use. Like if we just go f of n minus 1 plus f of n minus 2, then it will be 25 that we need to solve.
Okay.
If we had an algorithm which stores each and every value in a particular array or a list, then it will just take 6 months.
Okay, both you are right. So this is the essence or crux of dynamic programming. On the one hand, there are 24 subproblems. On the other hand, there are only 6 subproblems. Both are right. To solve the given problem f of 6, we need to solve 24 subproblems. But the 24 subproblems are all not distinct. If we count all duplicate subproblems to be 1, all F5s are counted as 1, all F4s are counted as 1, all F3s counted as 1, all F2s counted as 1, all F1s counted as 1, then we have only 6 distinct subproblems. So I may say the number of subproblems is 24, but the number of distinct subproblems is only 6. But as you have rightly observed, if we blindly implement Fibonacci number, computing the nth Fibonacci number using the recurrence relation, giving rise to this recursive algorithm, this recursive algorithm, FibR, will actually solve all the 24 subproblems. It is very blind. It does not recognize or take into consideration, oh, okay, for example, uh, the third call solves a subproblem f of 4. The 17th call also solves the same subproblem. But this version of the algorithm does not recognize, oh, this f of 4, this subproblem I have already met before in the third call. Therefore, I don't need to call it again. The third call was f of 4 and I computed the result, the output of f of 4. Therefore, I don't need to solve f of 4 again. This recognition is not with the recursive version of the algorithm fib-bar that we have calculated, that we have written. Therefore, we are motivated. Can we improve the algorithm, change the algorithm to take advantage of this observation, to exploit this observation? If a subproblem has been solved before, do not solve it again. Do not repeat yourself. Look at this. F of 5 is solved once. This algorithm, f of 4 it solves it 2 times. F of 4 is shown in blue. F of 3 shown in green is solved 1, 2, 3, 3 times. F of 2 is solved shown in red 1, 2, 3, 4, 5. F of 1 and f of 0 so many other times. So since we have observed that there is only a, even though there is a number of subproblems, the number of distinct subproblems is much fewer. We want to change the algorithm to take advantage of that. We call that memoization. There is no spelling mistake here. Remember everything. First time you solve a problem, store its solution in a table. We call that memoizing. For any subsequent instance of the same problem, for example, f of 3, we solve it first time, you store the result in a table. Second time f of 3 is called, the subproblem f of 3 is encountered, do not solve it, but retrieve the solution from the table. Third time, the subproblem f of 3 need to be solved, do not solve, but look up the table. That's it. Now we will solve a number of problems and do many things, but this is the crux. This is at the heart of DP algorithm. First time you solve a subproblem, store the result in a table. Second time, third time, fourth time, or any subsequent time, we need to solve the subproblem. Do not solve, but retrieve. Okay. With this very powerful observation, we can modify the algorithm as shown here. I have only copied, pasted fib bar. The only difference I have shown in red, line numbers 1, 2, 4, 5 are just copied from fib bar. The differences are if n is equal to 0, then return 0. Now I have put f of 0. If n is equal to 1, then return, instead of 1, I have put f of 1. There is a table. Zero, 1. This is initialized with 0. This table is called f, initialized with 1. And the subsequent things are not yet initialized. Let's say this is n. Formerly we wrote if the two base cases are not satisfied, then we will come to the recursion step. Recursion step is calculate fib of n minus 1, calculate fib of n minus 2, add them, that is a result. But now we are doing a very small change. The control will reach line 4 only when the two base cases are not true. If the control ever reaches line 4, calculate f of n as f of n minus 1 plus f of n minus 2 and store the result in a table. So maybe we calculate something and put the value here. Therefore, we do not immediately return fib m for memoize, fib m of n minus 1 plus fib m of n minus 2. We store it in a table before we return. But so this is a recursive call. But before we make a recursive call, we said a recursive call means solve. But before you solve, we have to check whether we have already solved the subproblem before. How will we check? Because every time we solve a subproblem, we store the result in a table. Whenever we come across the same subproblem, first look up the table, then solve. If lookup the table is success, there is no need to solve. If lookup table is failure, the subproblem has not been solved before. Only then we solve. How do we look up the table? If f of n is initialized, if f of n is not equal to this nil, okay? So f of n has a valid value, then return f of n. So lookup is successful. That means this is the second time, or third time, or fourth time, or fifth time we want the solution to the problem. If it is the second time, or third time, or fourth time we want a solution to the problem, we just retrieve the solution from the table and do not compute the solution. Okay, maybe two important words. This is retrieve the solution. This is compute the solution. First time, compute the solution. Subsequent times, retrieve the solution. And this recursive algorithm need to be called by a main algorithm which initializes f of 0 to 0, f of 1 to 1, and then we can call fib m of n. This is called memoization. All right, so let us take a look at the problems and subproblems. What are the problems? Fi has the subproblems Fi minus 2, Fi minus 1, and so on. F3 has the subproblems F2 and F1. F2 has the subproblem F1 and F0. F1, okay, this is not that. Oh, okay. This is not correct. And I have rearranged or ordered the subproblems in such a way, I have ordered the subproblems and drawn arrows between the subproblems. To solve subproblem F3, I need solutions to subproblems F1 and F2. Then I have drawn arrow. Okay, F1 is needed for F3 and F2 is also needed for F3. Suppose here I have F4. To solve F4, I need F2 solution and F3 solution. So these arrows show dependency. Fi depends on Fi minus 2 and Fi minus 1. So what does this graph show? The graph show the dependency among the subproblems. And you will note that all the edges in this dependency graph are only from left to right. There is no arrow in the opposite direction, right to left. Such a graph is known as directed acyclic graph, famously abbreviated DAG. So whenever the dependency between the subproblems is a DAG, directed acyclic graph, this problem is suitable to be solved using DP. This is very important. And instead of using recursion with memoization or memoized recursion did not solve 24 subproblems, it solved only 6 subproblems. That's a great advantage. We are expecting the running time of memoized recursion to be much better than the straightforward exhaustive recursion. So already we have achieved quite something. What we want to do now is, after all, we are solving a set of subproblems, and the subproblems can be ordered in this way so that the dependency is only from left to right. Then we say, oh, instead of solving the subproblems or computing the solutions to the subproblems using recursion, we can compute the solutions to the subproblem. In this way, they are ordered from left to right. First, compute the solution of f of 0, that is 0. Then compute the solution of f of 1, that is 1. Since they are base cases. Compute the solution of f2. Since we have already the subproblems on which f2 depends, that is f0 and f1. From f0 and f1, we can calculate f2. Then we come to f3. We have already solved f1 and f2, therefore we can solve f3. Okay, then come to f4. We have already solved f2 and f3, therefore we can come to f4. So if the dependency is a directed acyclic graph, there are no backward edges, there are only forward edges. There are only edges are only in one direction from left to right. There is no edge in the opposite direction, right to left. Then we can solve the subproblems from left to right. And that is what we do here. I call that Fibonacci DP. F of 0 becomes 0, f of 1 becomes 1, corresponding to base cases. Then all that we have to do is, for I is equal to 2 to n, we want to solve f of 2, f of 3, f of 4, and so on, f of n in that order. F of I becomes f of I minus 1 plus f of I minus 2. Since we have already solved f of I minus 1 and f of I minus 2, it is possible to calculate f of I. When we are done with that, return f of n. What is the difference between this memoization versus DP? In very simple words, memoization works bottom up or top down, sorry. To solve f of 6, solve f of 5, f of 4, then f of 3, then f of 2, f of 1, f of 0, and so on. Whereas here, this is bottom up. First solve f of 0, then f of 1, then f of 2, f of 3, f of 4, f of 5. Finally, f of 6. It is a matter of preference and taste. Both achieve the same thing. Okay? Very often, the dynamic programming version is easier to understand than memoized version. I think our preliminary discussion is over. What is the essential feature of dynamic programming? There is a large number of duplicates of problems. In this condition, solve a subproblem only once and store it in a solution. Subsequently, if solution to the subproblem is required, do not compute the solution but retrieve the solution. In practice, we implement it by ordering or arranging the subproblems in such a way that whenever we want to solve a subproblem, the smaller subproblems, okay, that's an informal word. For F3, F1 and F2 are smaller subproblems. For F4, F2 and F3 are smaller subproblems. For Fn, Fn minus 1 and Fn minus 2 are subproblems. So whenever we come to solve a subproblem, the smaller subproblems on which it depends are already solved. So arrange the subproblems from the smallest subproblem to the largest subproblem. The largest subproblem is the given problem. So, and solve them in that order. First solve the smaller subproblems, using them solve a larger subproblem, using them solve still larger subproblems until we solve the largest subproblem, which is the given problem. By the way, this Fibonacci number calculation can be improved slightly better. Do we really need a table to store the values? After all, every time we want to calculate an Fi, we need only two subproblems, two immediate predecessors, Fi minus 1, Fi minus 2. We are not interested in Fi minus 3, I minus 4, and so on. In that case, instead of maintaining them in an array of size n, it is enough to maintain only two variables. And that is what the version that you normally write. Don't remember everything after all. This version is motivated from DP because even though we are filling the whole table, actually we need only two entries from the table. Therefore, instead of maintaining the two entries in the table, maintain just the two entries in two variables f and g. Okay. We have done something very important, and let's take a review of what we have done. In decrease and conquer and divide and conquer, decompose a problem into a small number of subproblems. Solve each subproblem and then combine the solutions of the subproblems to the solution of the problem. That's the classical problem solving, algorithmic problem solving approach. In exhaustive search, decompose a problem into every possible subproblem. I have emphasized that a number of times. A few subproblems, every possible subproblem. Solve each subproblem and combine the solutions of the subproblems into a solution of the problem. In DP, decompose a problem into a sequence of overlapping subproblems. I want you to mark the highlighted words. A few subproblems, every possible subproblem, a sequence of overlapping subproblems. And starting from the smallest subproblem, construct solutions to larger and larger subproblems until we have a solution to the given problem. In exhaustive search, we decompose the problem into every possible subproblem. If you take the whole collection of subproblems, there is a large number of duplicates. This duplicates is what we call overlapping subproblems. What do you mean by overlapping? We have, suppose we have a problem P5, another problem P8. Here is a problem, let's say P3. P3 is needed to solve P5. P3 is also needed to solve P8. Suppose some P15. P3 is also needed to solve P15. So P3 is a subproblem of P5. P3 is also a subproblem of P8. P3 is also a subproblem of P15. Then we say this P3 is an overlapping subproblem. This is only another word for duplicate. P3 is needed for P5, P8, P15, therefore it is a duplicate subproblem, and just solve it once. In decrease and conquer, typically we have only one subproblem. Typo. And it is polynomial running time. It should be. In divide and conquer, we have a small number of subproblems, non-overlapping. They reduce the running time. There is already polynomial. If this is a big O of n squared, then it may reduce it to something like big O of n log n. Exhaustive search, there is a large number of subproblems and they may overlap. That large number may be exponential, a homoc. In f of 6, the number of subproblems we said is 24. A number of times a subproblem need to be, a solution to the subproblem needs to be computed. Okay. In general, what is this, for f of n, what is the number of subproblems? It's a homoc. Actually, you should solve the recurrence relation f of n is equal to f of n minus 1 plus f of n minus 2. We have not solved this recurrence relation before. This is a second order homogeneous recurrence relation. You have to look up any book on discrete mathematics to know how to solve such recurrence relation. Okay. So in exhaustive search, we have a large number of subproblems. They may overlap, but exhaustive search doesn't care about whether it overlaps or not overlap. We have an exponential number of subproblems. In dynamic programming, again, we have overlapping subproblems, but we do care about overlapping subproblems. The number of subproblems may be exponential, but the number of distinct subproblems may only be polynomial. We do not solve each of these exponential number of subproblems. We solve only that polynomial number of distinct subproblems. That is the reason why a DP results in a better running time than exhaustive search. Okay. Now, how do we solve? Given an algorithmic problem, how do we apply DP? Identify a set of subproblems. Step 1, I won't say step 1, okay. These are some of the features. Derive a recurrence relating the problem solution to solutions of its smaller subproblems. 2, the problem can be solved by solving a set of overlapping subproblems. 3, there is only a polynomial number of subproblems, distinct subproblems, but an exponential number of subinstances. Do not solve each instance of a subproblem, but solve each subproblem only once and store the solution in a table. Whenever the solution to a subproblem is needed, look up the table and retrieve. Do not compute every time. Do not compute but retrieve is the slogan. There is a natural ordering on subproblems from the smallest to the largest. With the recurrence relation, calculate the solution to a subproblem from the solutions to some number of smaller subproblems. And there is an idea called principle of optimality, as an optimal solution to any instance of an optimization problem is composed of optimal solutions to its subinstances. State the principle of optimality. If the solutions to the subproblems are optimal, then the solution to the problem constructed from these sub-solutions is also optimal. If any problem exhibits this nature, it is said to have an optimal substructure and obey principle of optimality. Okay, let us, this is important. Steps to design a DP algorithm. 1. Identify the subproblems. Intuitively, you should get an idea of what could be the subproblems for a given problem. It is not always straightforward. If it is an array-based algorithm, you will say, okay, to solve the problem for an array of size n, reduce it to an array of size n minus 1. Something like that. Life is not that easy all the time. Identifying suitable subproblems takes experience and creativity. It is not just, there is no formula for that. Then, once we have identified the subproblems, find a recurrence relation between a subproblem and the smaller subproblems. I don't say a problem and a subproblem and the smaller subproblems required to be solved. Very importantly, identify the variables of the recursion. Sometimes we may recurse on one variable. Other times we may recurse on two or more variables. Step back and see if the subproblems overlap in the overall recursive process. When you write the recurrence relation, you should also identify the base cases. I have sung and danced about it. Whenever you write a recursive algorithm, you should have at least one base case. Then design the table to store the solutions. Sometimes it may be a 1D array. Sometimes it may be a two-dimensional array. You may call that a table. Sometimes it may even be a 3D array. That depends on how many variables we recurse. If we recurse on one variable, maybe it is 1D array. If we recurse on two variables, it may be 2D array and so on. After we have designed the structure, whether it is 1D or 2D, we should decide the order in which we are going to fill in entries in the table. Order the subproblems so that always smaller subproblems are solved before the larger subproblem. This is very critical, deciding the order. If it is a 2D array, do we have to fill in row-wise and each row from left to right? Or do we have to fill in column-wise, each column from top to bottom? What is the order? So first, identify the subproblem. Second, the recurrence relation, which includes the base cases. 3, the table and the order in which the solutions will be computed and filled in the table. And finally, you will write the algorithm. Don't jump in to write the algorithm. And lastly, you will analyze the running time. So I may say these are 5 basic steps. Subproblems, recurrence relation, table, and algorithm. When you are asked to solve a problem using dynamic programming, all that you do is to write an algorithm that is of no use. There is more science in the recurrence relation and the table and the order in which the table entries are filled than in the algorithm. If you just present an algorithm without giving the recurrence relation and the table and the order in which the table entries are filled, that algorithm is as good as useless. Okay, one more small example and then we will wind up for the day. Binomial coefficient is a very important number in combinatorics. The binomial theorem states a plus b to the power n is equal to n choose 0 a power n plus n choose 1 a power n minus 1 b and so on. In general, the binomial coefficient is n choose k a to the power a n minus k times b to the power k, and the last term is n choose n b power n. The problem is we want to calculate, given two numbers n and k, we want to calculate the binomial coefficient n choose k, or some notation is n choose k. What are the subproblems? To compute n choose k, we need both n minus 1 choose k minus 1 and n minus 1 choose k. I mean, this is not a great problem. In general, even to identify, recognize the subproblems takes time. It takes experimentation, flair, and some creativity. But this is such a straightforward problem, therefore there is no experimentation or creativity involved. N choose k has the recurrence relation n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k for n greater than k greater than 0. Okay. If k is equal to 0, n choose 0 is equal to 1. Similarly, n choose n is also equal to 1. This is simply another notation. C of n comma k is equal to C of n minus 1 comma k minus 1 plus C of n minus 1 comma k for n larger than k larger than 0. C of n 0 is equal to 1. C of n comma n is equal to 1. We don't need to do this, just to reinforce the point that if we straightforwardly, we can implement this definition of binomial coefficient as a recursive algorithm in a blind way. If we blindly implement the recurrence relation into a recursive algorithm, this is what we will get. For example, C of 5 comma 3 is C of 4 comma 3 plus C of 4 comma 2 and so on. C of 4 comma 3 is C of 3 comma 3 plus C of 3 comma 2. This is a base case. This is equal to 1. Since C of 3 comma 2 is C of 2 comma 2 2 comma 1. This is a base case 1. 2 comma 1 is 1 comma 1 1 comma 0. Both are base cases and so on. I have just illustrated one subproblem with duplicate. C of 2 comma 1 had 3 instances. Here is the C of 2 comma 1. Here is another C of 2 comma 1. Here is another 2 comma 1. The subproblem is C of 2 comma 1. A blind recursive algorithm computes the solution to C of 2 comma 1 3 times. Okay. Therefore, okay, these are overlapping subproblems. Now for design. Recursion on two variables n and k. Therefore, we need a two-dimensional array to store the subsolutions. When do we say a subproblem is smaller than a given subproblem? Since a problem is given in terms of n and k, suppose n is reduced to n minus 1, even if k is not reduced, that's a subproblem. N is not reduced but k is reduced, it will be a subproblem. N minus 1 and k minus 1 is also a subproblem. We don't have this here. So either in n or both in n and k. N minus 1 or both n minus 1 and k minus 1. we said we have to choose a table structure, we should also choose the order. N minus 1 should be solved before n. Okay. By 2D, I mean, suppose this is n and this is k. N may be from 0, 1, 2, and so on, n, and k may be from 0, 1, 2, and so on, n. In what order we have to choose? Suppose this is k, this is n. N minus 1, the subproblem with n minus 1 should be solved before subproblem with n. Okay. That imposes an order. K does not impose an order. Therefore, rows with smaller value of n should be computed before larger values of n. So we have to calculate n is equal to 0 first. How you calculate? Okay, in a given row, do we calculate small case first or large case first? Doesn't matter, because we have n choose k, n minus 1k plus c of n minus 1 k minus 1. The order of k does not matter. Similarly, after this, n is equal to 1 row has to be calculated. After this, n minus n is equal to 2 has to be calculated. Finally, so in a n by k table, vary row from 0 to n. Rows in the rows are indexed by n. For each row, vary column in any order. Let us choose to vary from 0 to k. And the base cases are n choose 0 is equal to 0 for all values of n. That is, this column should all be 0. So initialize c of I is equal to 0, I comma 0 to 0. Similarly, n choose n is equal to 0. Initialize c ia is equal to 0. C ia is equal to 0 will be these diagonal elements. So row wise from row 0 to row n, top to bottom, in each row column wise from column 0 to column k. Oh, this is a typo. All right. So this is the order we mean. First calculate this, then this row, n is equal to 2, you calculate this, n is equal to 3, you calculate this, n is equal to 4, you calculate this, n is equal to 5, n is equal to 7. Before that, you first initialize this column to 1. N is equal to 1 0, 1 1, 2 1, 3 1. Sorry, this is 1 0, 2 0, 3 0, 4 0, 5 0, 6 0. The answer is 1. Similarly, C of 0 0. I have shown the order here: A B C D E F G H I J K L M N. And if you take an example, let's consider this. N depends on n minus 1 k and n minus 1 k minus 1. So it depends on, this is n minus 1th row, this is kth column, this is n minus 1 And so 9 is calculated from 5 and 6. Like this, I have shown here. C of nk is solved using C of n minus 1, k minus 1, and C of n minus 1, k. So every entry is calculated from 2 entries from the preceding row, from the row above that. The 2 entries come from, okay, one of the 2 entries comes from the same column, the other entry comes from the preceding column. So we have designed the algorithm. We started with the recurrence relation. Then the table structure, then the order in which the subproblems, okay, one, what are the subproblems? How are the subproblems related? What is the table structure? What is the order? Only after we have done this design, we have to write the algorithm. Binomial n comma k, 2 non-negative integers n and k satisfying this relation, n larger than or equal to k, larger than or equal to 0. Output is C of n comma k. Okay. This is initializing all C of I comma 0 is equal to 1. For all values of n, I is equal to 0, 1, 2, and so on n, then all Ci comma I is equal to 1 for all values of 0, 1, 2, n. Then for I becomes 1 to n, this is from row 1 to row n. Okay. For j becomes, this is row wise. This is fill the columns. Take a look at this. For j becomes 1 to, maybe you may wish to write j becomes 1 to n. Why you should not write n and you have to write minimum of I and k? You have to think. Ci comma j becomes Ci minus 1 comma j minus 1 plus Ci minus 1j. This is simply the recurrence relation we have already formulated. After we have filled in the table, that is after we have computed solutions for all the subproblems we have identified, the subproblem that we are interested in is C of n comma k. Okay, return that. I leave the analysis to you. It will be big theta of nk. Let me stop here.